So we had looked at a single particle in a volume V, and we determined that the canonical partition function of this single particle is V over lambda t, consistent with our classical result. Now what we want to do is we want to look at the n particles in a volume V given by LQ, and we want to calculate the canonical partition function. So we start off with the density matrix rho hat. But first, before determining that, we note that for this n particles in a volume V, so now we want to look at n particles in a volume V, and this is still a non-interacting system. Our idea is to calculate the n particle partition function z of tvn and see what result that we get. The many particle wave function psi of r1, r2, rn can be constructed from the single particle wave function phi k1 r1, phi k2 r2, all the way phi kn rn. So that if I want to evaluate the density matrix, and we will write down this as k1, k2, kn e to the power minus beta h bar, k1 prime, k2 prime, kn prime is given by k1, k2, so we now want to look at n particles in a volume V is equal to, it keep the same setup except that now I have n particles and it is still a non-interacting system, so that the Hamiltonian, the n particle Hamiltonian is sum over I pi square over twice m. Our goal is to calculate the n particle canonical partition function. So we start off by constructing the many particle wave function from the single particle wave functions, which I know. For a single particle, I know that this was my wave function, right, which was square root v e to the power I k dot r. So I can construct the single particle wave function as phi k1 of r1, phi k2 of r2, so on, all the way up to kn rn, which is equal to product over I phi ki ri. The density matrix, so now we will interchangeably use phi k is identical to this. So the density matrix k1, k2, the density matrix, if I want to calculate this, kn is e to the power minus beta h, k1 prime, k2 prime, kn prime, and it's very easy to do that, and therefore you immediately see that this is going to be k1, k2, kn. You put in the Hamiltonian from this expression is minus beta sum over I pi square over twice m, k1 prime, k2 prime, kn prime, and this becomes e to the power minus beta h bar square k square over twice m, k1 square. So let me just write down this first as h bar square over twice m, k1 square plus k2 square, kn square. And the normalization, orthonormalization of this, essentially since they are orthonormal, gives you delta k1, k1 prime, delta k2 prime, k2, so on, and delta kn prime, kn. Now the partition function follows from the normalization of the density matrix, and this is tvn sum over k1, k2, kn, k1, k2, kn, we'll write down this as sum over I ki square over twice m, k1, k2, kn. So this is product over I. So you can split this because the exponential splits into products, and then you have k1. So let's write down this explicitly first, and then you'll see this is going to be k1 minus beta h bar k1 square over twice m, k1, k2 e to the power minus beta h bar square k2 square over twice m, k2, so on and so forth. And therefore there is also a sum over k1, k2, kn, which also splits, and therefore you will have product over I equal to 1 to n, or in more compact form. So let's say sum over ki e to the power minus beta h bar square ki square over twice m, ki, and this is simply sum over k e to the power minus beta h bar square, since it's just a number now, beta h bar square k square over twice m raised to the power n. And this we evaluated for a single particle case, so this is going to be v over lambda t raised to the power n. So your z of tvn is this quantity, the canonical partition function. Note that this is different from the classical partition function. How is it different? Because it does not have the 1 by n factorial that we included. So the 1 by n factorial does not come in quite naturally within the theory. So therefore this still does not resolve the issue that the particles are indistinguishable. So in this particular picture we say that particle 1 has momentum h bar k1, 2 has momentum h bar k2, and so on and so forth. But in reality that is not the case, because if I interchange the indices, the particle indices, nothing changes in the system. But clearly that somehow has to be incorporated more carefully when we construct this many particle wave function. So our starting point was this many particle wave function, and clearly we see that this still does not resolve the issue of the indistinguishability. So the density matrix in the coordinate representation is r1 prime, r2 prime, rn prime, rho hat r1, r2, rn. And then we introduce the completeness of the vector. I'm going to compactify the notation. I'm going to write this as k1 prime, So ki prime sum over and ki, and I have r1 prime, r2 prime, rn prime, k1, k2, kn, k1, k2, kn, e to the power minus beta h bar, k1 prime, k2 prime, kn prime, and then I have k1 prime, k2 prime, kn prime, r1, r2, rn. I know this quantity now, so this is going to be sum of ki prime, ki, all the values of ki. Further, I'm going to compactify this notation ki, where this set is identical to r1 prime, r2 prime, rn prime, and so is this one with k1, k2, kn, and this is going to be e to the power minus beta h bar square over twice m sum over I ki square, and this is going to be your k prime I. Wait, we have missed one crucial thing, that is the delta functions, delta k1, k1 prime, delta k2, k2 prime, all the way delta kn, kn prime, and then we have ki prime and ri. So one can just do the sum over the delta function, then I'll be left out with, let's say, sum over k. I will have ri prime, ki, e to the power minus beta h bar square sum over I ki square, and then I have ki ri. So that this is sum over k. This is the wave function, many particle wave function in the coordinate representation, so that I'm going to have product over I phi k I ri e to the power minus beta h bar square over twice m sum over I ki square, and this is going to be phi star ki ri. So the product over I and the sum over k can be converted into an integral, and if you do this, I will, so let's just first write down this step, sum over k I phi ki ri e to the power minus beta h bar squared over twice m ki square phi ki star ri, and this sum can now be, because this exponential can be written as a product of exponentials, right? Because I have a sum of in the exponential, therefore it splits up into products of this term, and therefore if you now evaluate this, you are going to get 1 by v e to the power minus pi r prime I minus ri whole square over lambda t square. So this is your coordinate, this is the density matrix in your coordinate representation, ri prime rho hat ri. Still, here also the problem is still there. There is no n factorial. So essentially our construction of the many particle wave function does not resolve the problem with the indistinguishability of the particle. The many particle wave function that we constructed had the form R1, R2 all the way up to Rn was product over I phi ki Ri. This is an eigenfunction of the Hamiltonian. So if you write down this is going to be E psi, where E is going to be sum over I h bar square k square over twice m, ki square over twice m. Even though this is an eigenfunction of the Hamiltonian, any wave function that you get by renumbering the particle indices is also going to be an eigenfunction of the Hamiltonian. So for example, if I have R1, R2, Ri, Rj, Rn, if I interchange I and j, this becomes psi of R1, R2, Rj, Ri, Rn. This will remain, this will be a eigenfunction of the Hamiltonian, because even though I have interchanged I and j, nothing in the system has changed. Your system remains the same, correct? Now the indistinguishability of the particles is closely related to the invariance of the Hamiltonian with respect to this change in enumeration in the particle index. So clearly this operation of interchange of indices I can define as an operator which does that. And therefore, it's obvious that this operator commutes with the Hamiltonian, so that one can construct the eigenfunctions of the Hamiltonian in such a way that it is also an eigenfunctions of this operator. So let the symmetry operator which commutes with the Hamiltonian and essentially which belong to the invariance on the Hamiltonian with respect to change in enumeration of particle indices be p hat ij. So this operator exchanges ith and jth index, so that p hat ij psi of r1, ri, rj, rn is going to be psi of r1, rj, ri, rn. And this commutes with the Hamiltonian for all I and j. We now wish to determine the eigenvalues of this operator. So p hat ij psi of r1, ri, rj, rn is going to be lambda times psi of r1, ri, rj, rn. But this operation gives me psi of r1, rj, ri, and then I have rn is lambda times psi of r1, ri, rj, rn. If I operate again p hat ij from the left hand side to this equation, then I have p hat ij, p hat ij. The right hand side is going to be lambda square of psi, R1, Ri, Rj, Rn. The left hand side is, what will it do? It will again interchange this and put it back here and bring it over here, so that you have R1, Ri, you get back the original wave function that you started off with. And this essentially tells you that lambda square is equal to 1, so that lambda is equal to plus minus 1. So it can have either a plus 1 eigenvalue or a minus 1 eigenvalue. Lambda is equal to plus 1 corresponds to a symmetric wave function, and lambda corresponding to minus 1 corresponds to an anti-symmetric wave function. So it is now clear what we are trying to do. We started off this naive wave function that we had constructed from the single particle wave functions, and we realized that the canonical partition function is definitely not like the classical one that we had derived. There is a 1 by n factorial which is missing, and we know that this 1 by n factorial essentially comes from the indistinguishability of the particle. And this indistinguishability is very closely related to the operation of interchange of particle indices. So there is a symmetry. So Hamiltonian is invariant under this operation. So there is an operator which essentially commutes with the Hamiltonian, and therefore one can construct eigenfunctions of the Hamiltonian in such a way that these are also eigenfunctions of the same, of the symmetry operator, of this exchange operator, right? And therefore one tries to, so what is one trying to do over here is, one is trying, from this naive wave function that we see, we are trying to construct wave functions with definite symmetry. The generalization of this exchange operator is the permutation operator. Operator p hat, so that p hat times psi r1 rn is going to be psi of rp1 rp2 rpn, where p1 p2, so this is not the momentum, perhaps this is a very poor choice of syntax, but let's see. Pn is a permutation of the numbers one, two, n, and there are several possible permutations which are there. So if one starts with this wave function psi of r1 rn, which does not have a definite symmetry, I can construct a symmetric wave function, an antisymmetric wave function and a symmetric wave function by using the permutation operator. So this is going to be a sum over p hat psi of r1 rn, and this is going to be, so starting from the many particle wave function without any definite symmetry, which was product over I phi of ki ri, we can construct wave functions which are symmetric wave functions Rn by operating the permutation operator on psi Rn, and the sum over p. The sum over p essentially means sum over all possible permutations of these numbers 1 to n. And the antisymmetric operator, the symmetric operator has an eigenvalue 1, therefore it does not matter over here, but the antisymmetric operator will have an eigenvalue minus 1, so that this is going to be minus 1 raised to the power p psi of r1 Rn, right? Once again, there is a sum over p, which is a sum over all possible permutations. Now, the sign minus 1 raised to the power p is defined as minus 1 raised to the power p is equal to 1 if there are even permutations and is equal to minus 1 if there are odd permutations. Now, even permutations or odd permutations refer to number of exchanges that you need to do to obtain a certain permutation of the numbers 1 to n, right? So if you need to do 4 permutations to get to the desired set of p1, p2, pn, then it's an even permutation. If you need to do 5 exchanges to get to the desired set of p1, p2, then it's an odd permutations, because all these wave functions, there is a sum over p, all possible permutations that you can imagine with of the numbers 1 to n. A wave function which is a symmetric wave function is what are called bosons, and the antisymmetric wave functions are the ones for particles which are called fermions. So starting from a system where particles were simply identified by the indices, even though they were indistinguishable, we see that if we construct particles of definite symmetry, we are looking at 2 different kinds of particles. Particles which have even wave functions are called bosons, and particles which have odd wave functions, or not odd wave functions, but antisymmetric wave functions are called fermions. So we have psi of symmetric k1, k2, kn, r1, r2, rn is equal to, so we'll just rename the normalization a plus a and b as sum over as n. So we'll rename a as n plus sum over p, all possible permutations, the permutations operator operating on phi k1 r1, phi k2 r2, phi kn rn. And similarly, the antisymmetric wave function of k1 kn, we have r1 r2 rn is going to be n minus sum over p minus 1 raised to the power p hat operating on phi k1 r1, phi k2 r2, phi kn rn. So for our benefit, we are going to write down this in a direct notation, which would mean that k1, k2, kn, the symmetric wave function is n plus sum over p hat k1, k2, kn. and the antisymmetric one is going to give me n minus sum over p hat minus 1 raised to the power p hat k1 k2 kn. So we have to determine the normalization constants n plus and n minus, right? So let's try to do it at one go. Symmetric as well as antisymmetric, symmetric as well as antisymmetric is n plus minus whole square. I will have over p prime. So two possible permutations, and then I'm going to have k of p1, k of p2, k pn, k p1 prime, k p2 prime, k pn prime. Note that the total possible permutations of this number 1 to n is n factorial. So what one can do here, because this is an inner product, so one can take this and simply replace the sum kp1, kp2, kpn. We can replace this sum by n factorial times k1, k2, kn, and this we can do because this is an inner product, so that our normalization, essentially this means that I have ki, I have symmetric and antisymmetric wave function, symmetric and antisymmetric wave function. This becomes n plus minus whole square n factorial. I'll be just left out with one sum over k1, k2, kn, kp1, kp2, kpn. So now we bring in the concept of the occupation number. So we have the occupation number n of k. So which means that there are n1 particles in k1, n2 particles in k2, so on and so forth. Now here you note that this inner product is 0 unless it corresponds to the original unpermutated order, and that only happens in k factorial times number of particles which are there in the level. So this quantity ki, take this simple form of n plus minus 1 whole square n factorial product nk factorial over k. This implies that your n plus minus square n factorial product over k nk factorial is equal to 1. For fermions, nk can be either 0 or 1 because of the symmetry of the wave function. So this implies that n minus is going to be square is 1 over n factorial, which implies n minus is 1 over square root n factorial. For bosons, there is, which have the symmetric wave functions, there is no restriction of nk to be either 0 or 1, it can be anything. So therefore n plus becomes 1 over square root of n factorial product over k nk factorial. Therefore, for fermions, in terms of the single particle wave functions, the many particle antisymmetric wave function takes the form 1 over square root of n factorial, determinant of the matrix phi k1 r1, phi kn r1, phi k1 rn, phi kn rn. And this determinant is what is called a Slater determinant. From this form of the wave function, it is clear that the fermions obey Fermi's exclusion principle, which states that two fermions, two equal fermions, cannot occupy the same single particle state. For if that was the case, then you see that two of the quantum numbers in the set k1 to kn would be equal, in which case two of the rows in the determinant are going to be equal and the wave function identically vanishes. For bosons, it's slightly more complicated because they do not have the restriction nk is equal to 0 or 1. Many particles can occupy the single particle state, and therefore that makes a normalization a little more complicated that we have seen. And essentially one has to see of these quantum numbers k1, k2, kn, how many of them are equal. So if there are n1 particles, if there are n1 particles in k1 and n2 particles n2 particles in k2, so on and so forth, then you see this inner product contributes to the sum only nk factorial times, and therefore the normalization becomes n factorial product over k nk factorial, where n factorial is the total possible number of permutations you can have.